Welcome. In this video I'm going to be talking about 5-volt power supplies, specifically USB style 5-volt power supplies. So as I've evolved my electronics lab, I've run into lots of equipment that uses a 5-volt power supply. Things like my new Eakins inspection scope, various Raspberry Pi projects, various cameras. Lots of stuff is powered off of 5-volt directly. It used to be in the olden days you'd power something off of 9-volt or 12-volt, have an internal voltage regulator, but lately the trend seems to be to just make things powered off of 5-volt. So what I thought would be really cool is if I had some kind of a power distribution system, where there was a bunch of USB outlets on my wall and I could plug equipment in and the equipment would be powered and I could switch it on and off. First I looked to see if there was an existing solution. I couldn't find anything that was just like a big USB power strip. The closest thing I could find is something like this. It's a bunch of switches. There are 4 USB outlets. There's a barrel jack on the side where you can supply power or you can supply it via USB. It's actually a USB 3.0 hub, which I wouldn't use the hub functionality in it. I would just use the power switching. So I actually did take this thing apart. I looked in it. I put 3 amps through it and verified it didn't burn up. So I was almost going to do that. I was going to buy 3 or 4 of these, put them around the bench, and be able to turn things on and off. The problem I ran into with this, why I didn't go with this solution, is there's no isolation between one port and the next. So if I take and I hook my expensive $300 or $400 inspection scope up to one port, then I hook one of my haphazardly designed Nixie tube clocks into another port, and the Nixie tube clock somehow backfeeds 300 volts into it, I fry all kinds of equipment. Who knows what's going to happen? So I kind of like isolation between ports, and for that same reason I'm rejecting this style of adapter. This has 4 ports. I've been using this to do everything from charge my iPhone to run my inspection scope lately, but there's no isolation, there's no switches. So I basically set out to design my own, and I'll be showing a few prototypes later and working through the design process. So here are a couple of the things I built, but let's kind of look at what the requirements are that I set out with this project, and then we'll see how that drove the design that I ended up with. So first thing is, I'm going to power the thing from a common 12-volt supply, because I've got lots of 12-volt wall warts and desktop supplies and stuff laying around, in the 5 amp range or so, that it'd be great for powering a string of USB type power supplies. So rather than, making a bunch of things that ran off of, each one of them ran off of AC, I'll just start out with 12-volt DC, and we'll regulate that 12 volts down to 5 volts. So the main basis of this is going to be a standard switching regulator. We're going to go with a switching regulator for efficiency. So then you need overcurrent protection. If we, hook our 5-volt regulator up to something and it draws more current than we expect, we want to blow a fuse or something. So most basic overcurrent protection that everyone's familiar with is a fuse. A fuse has a little calibrated piece of wire in it. When you exceed the current rating, the wire melts, the circuit is disconnected. We'll do something smarter than that, but that's basic overcurrent device. The next thing we want is an overvoltage protection device. So let's say something went horribly wrong in our regulator, and the regulator, instead of regulating down to 5 volts, some part of the regulator burned up and it shunted the full 12 volts into here. That would destroy our piece of equipment that's connected to it. So if we add an overvoltage protection circuit, we can protect ourselves against catastrophic regulator failures. A common circuit that I found online is the crowbar circuit. Crowbar is basically a Zener plus a silicon controlled rectifier. And I'll go over this in the schematic in a moment, but what happens is the Zener, you select for a certain voltage, like 5.1 volts. If your voltage exceeds that, then it starts sending some voltage to the SCR. Once you hit a certain threshold, say 600 millivolts, the SCR will trip. And the SCR will stay tripped until its voltage source is removed. And the SCR is going to shunt the entire voltage down to ground. It is going to instantly blow that fuse. The reason it's called a crowbar is this dates back to, I don't know if this is for real or this is just urban legend, but supposedly people in an emergency when working on high-powered electrical distribution, if something went wrong, someone would take a crowbar and they would throw it across the rails. That would short things out, that would blow the fuse. So I didn't look in to see if that's actually true or it's just an urban myth. It seems very dangerous to throw crowbars across high power supplies. One could imagine the crowbar, molten chunks of it flying everywhere. It just doesn't sound like a good idea, but maybe, as a last resort, maybe people actually did that. But, that's the crowbar circuit functions similarly. It's a last resort. Something went horribly wrong, we'll short the whole thing out and we'll blow a fuse. So I'm going to do a little demo of the crowbar circuit. This is a prototype of the crowbar circuit that I used while trying this out so I could learn how they work. It's just the SCR, the Zener, the resistor, the capacitor, etc. And we can see right now my bench supply is putting out 5 volts and it's in constant voltage. So 5 volts just fine. There's 5.1 volt Zener. As soon as I start ramping it up, we'll start to develop a voltage on the other side of that Zener. So 5.2 volts is fine, 5.3. See there, we've got a little bit of current flowing through that Zener. 5.5, so got that little bit of current. 5.6. And now, as I said, the SCR is going to trip when it gets to around 600 millivolts. So if our Zener is 5.1, we should expect it to trip somewhere around 5.7. So, whoa there. So I turned it up to 5.7. It's tripped. The power supply went down to constant current mode. It tripped the power supply's current limiter. This thing is currently shunting 3 amps. It's getting very hot. If there was a fuse here, the fuse would have blown. Finally, our last stage is transient voltage suppression. So this is essentially a big Zener diode that's capable of shunting a decent amount of power. And it serves 2 purposes. One is if all else fails and something goes wrong, the TVS diode can shunt like 3 amps or more down to ground. Not so important because we already have the overprotection, but the other function of this is to actually deal with what happens if the fuse blows. So, if something weird happens, the fuse blows or the power goes out, there's various inductors in here, and these inductors can kick off an inductive spike, and that inductive spike, could spike this rail temporarily up to, like 10 volts or something. It's just for a fraction of a second, or even a fraction of a millisecond. But a transient voltage suppression diode can take any transients like that, those inductive spikes, and shunt them down to ground. Seems like a good idea in power supply design. It's actually recommended by one of the E-fuses that I'll be showing a data sheet on later. My first prototype is right here, this one, and this is the good old LM2576, which is this regulator right here. So I've used the LM2576 many times in the past on various supplies. It's a good switching regulator. It's maybe like 75% efficient. It can handle a wide variety of supply voltages. There's 5-volt versions of it. There's 12-volt versions of it. There's adjustable versions. It's an older regulator. It's not like super efficient, but it does get the job done. So yeah, so this whole circuit here would make up the regulator. So it's a switching regulator. So it's got an inductor. You'll see extra footprints in my schematics. That's because typically I want to be able to accommodate a couple different inductor footprints. So this is not really 2 inductors in parallel. It's just 2 footprints. You choose one or the other. But so your voltage regulator would have the IC. It's got an inductor. It's got a big diode. And it's got some capacitors on the output. Then this little section in the middle is a filter. That filter came directly out of the LM2576 datasheet, and it says if you're getting, too much peak-to-peak jitter on your output, add this little inductor capacitor filter, and it'll get rid of some of that switching noise. So it's 20 microhenry inductor, 100 microfarad capacitor. Again, straight out of the data sheet, that just gives us some cleaner output because switchers are inherently kind of dirty. And then we have a fuse. So you'll see 3 footprints here again. That's one is for a glass fuse, the other 2 are for PTCs. And that was just to accommodate a few different design options. Once I got the circuit boards, I could, play around with it a bit. Over here, we have the crowbar. So the crowbar, we've got this Zener diode. Again, there's a couple of footprints because I wanted to accommodate a through hole or a surface mount one. You've got the SCR. You've got a little capacitive filter here that lets you kind of control how sensitive the crowbar is. And so basically, when this voltage exceeds the threshold on this Zener, this line here starts to go positive. And once that hits like about 600 millivolts, this SCR will trip. So if we use a 5.1 volt Zener, then it will trip at 5.7 volts. That's approximate. There's some fluctuation in when an SCR will trip, so depending on temperature and other factors, could trip a little sooner, a little later than that. And then over here, I've got some status lights. So I've got a green light that says everything's good, and a red light that says the fuse blew. So finally, up here, we've got the USB jack. And that's our power output, so that we can plug in various USB style devices. So the USB 4 pins, 1 pin is ground, 1 pin is 5 volt. Those should be obvious. What's going on here in the middle is a little more interesting. That's the data in and the data out pins. If you look at various charger designs, what a lot of the manufacturers did in the olden days is they set up certain dividers to put certain voltages on these pins, and then the device could determine how much current to draw from the charger. So this in particular is from an Apple charger, these 43.3, 75, 49.9 resistor values. And I believe it was maybe a 1 amp Apple charger. I would have to double check that. But so the Apple device, if it sees those particular voltage levels on those pins, it'll know to draw that specific amount of current through the USB port for charging. It's a really, really hackish solution. They've got better communication chips now, but I figured why not throw this in and make my power supply look like a 1 amp Apple charger. This was my very first prototype, so we can see here's our LM2576, here's its big inductor, here's its big diode, there's various capacitors scattered around, here's the filtering inductor, the filtering capacitor, the USB port with those 2 resistor dividers, a PTC fuse. I went with that over a glass fuse so it would automatically reset. And I tried this thing out. This thing worked pretty good, but there were a few things that I didn't like about it. One of the things I didn't like was the PTC fuse itself. So PTC fuses, they have some unfortunate characteristics. Depending on how much current you pull, will determine how soon it trips. So if you pull just a little more than the rated current, it might take like tens of seconds for this thing to trip. If you pull like way more, then it'll trip instantly. It's not a very sensitive device. It's also got like this huge window between the hold current and the trip current, usually like about doubles. So if you get a device with a hold current of 1.35 amps and a trip current of 2.7 amps, and that entire window between 1.35 and 2.7 is sort of undefined. It might trip, it might not trip. So if I wanted to build a 2 amp charger, it falls right into the middle of that range. And so, you've either got to optimize for one side or the other. You've got to say, I definitely want it to trip at this value, or I definitely want to be able to hold that much. And then you've got that whole fuzzy zone there in the middle. I played with this, I didn't really like it. So that was the fuse selection. And then the crowbar uses this SCR, and down in here is the Zener diode. Like I say, I tried this out, it worked. I put my load tester on it, the PTC. I actually ran a bunch of experiments to figure out when the PTC trips and how long and various things. And like I say, I didn't like it real well. So I set about to make a second iteration of the design. And this is my second iteration. It's a little more complicated. So the regulator is over here in this section. Pretty much does the same thing that the LM2576 did, though this is an ACT 4533. It's a much more modern regulator than the LM2576. It's used in lots of recent products. Like I think there's actually an Apple charger that uses that IC. And it comes with a current limiting feature. So there's a current limiting resistor in there. It's got actually an overvoltage protection. It's higher frequency. It's much more efficient. I think it's up to like 91% efficient. But all of this, I'm not going to dive into it because it's all straight out of the data sheet for the ACT 4533. You look at the data sheet, and I pretty much copied their component values for a 5-volt USB charger. I did actually decide to tweak the voltage up a little bit. I raised it to 5.12 volts. That's because you've always got a certain amount of loss in the cable between a power supply and a device. And, going 5.12, it's still within tolerances of what the USB spec is, which I think says you can go all the way up to 5.25. But that 5.12, that, gives you a little bit more wiggle room for voltage drop in your cabling. So that was the regulator. So I actually kept that filter off of the LM2576 datasheet, that inductor capacitor filter. Smooth out that jitter in the power supply output. Seemed like a good idea. Why not? Then, where things get really interesting is the E-fuse. So the E-fuse is this TPS2421. It's actually called a hot swap controller. Hot swap is the process of plugging devices into a computer that's under power. So think something like a RAID, where you would just plug a hard drive in while it's running, stuff like that. And these hot swap controllers, typically they have an overcurrent protection feature, where you can dial in a certain current limit, and they will shut down if that current is exceeded. That's to protect the host computer and to protect the peripheral that's being plugged in. So I pretty much copied all this off the TPS2421 datasheet. So basically, the important thing that you need to know is that it's got a resistor right here. And this resistor sets the trip point of that hot swap controller. So if this resistor will determine a current, if that current is exceeded, this thing will shut off its output. Behaves just like a fuse. It remains shut off until you reset it. There's actually somewhere in here, probably this capacitor, there's like a time delay. So you can kind of like get yourself sort of a slow blow behavior based on that capacitor. Determines how quickly it will trip in the overcurrent, because sometimes there's just a little bit of transient overcurrent. It's got some status output lights. That's really neat. It gives me the red and the green LED. So unlike the PTC fuse that I said had that huge window between 1.35 and 2.7 amps where its behavior was undetermined, this thing you can dial in a specific current that it'll trip at. It's very sensitive, responds to that current. I do have the TVS diode. So the TVS diode was recommended by the datasheet for the TPS2421. They specifically mentioned when this thing tripped, if there's high current, there will be inductive fields. There will be those fields will lead to an inductive spike. And they said, put something like a TVS diode in. And I actually put one on both sides. So this one protects inductive spikes going out to the peripheral. This one protects inductive spikes going back toward the source power. And then finally over here we have our crowbar. Same crowbar circuit as before. We've got the SCR, we've got the Zener diode. So here is the completed power supply module. I'm going to kind of trace through it from the input to the output. So power comes in through this jack. We have a 100 microfarad filtering capacitor. Then we go into the voltage regulator section, which is all through here. So the ACT 4533 regulator chip is there, as well as its diode here, the SK54 diode, and the inductor. There's various filtering capacitors like this one here next to it. There's some resistors around which set the output voltage, set the current limit. Out of that we come out into some more capacitors. I've got a total of 3 of them in here, 10 microfarad ceramic, 220 and a 470 microfarad electrolytic. From there we go up into this second stage of filtering to reduce the ripple. So we've got another inductor here, I believe a 22 microhenry inductor, and a 100 microfarad capacitor. So from there we go up here to the electronic fuse. So this is the TPS 2421. It's this surface mount package. It's got a filter capacitor, a delay capacitor, and then a resistor to set the current limit, which is this potentiometer. We come out of that and we go over here into the crowbar circuit. We have our silicon controlled rectifier, resistors over here to do some filtering on the power going into the trigger, as well as 5.1 volt Zener diode. We've got the USB jack up here, as well as 4 resistors that set the voltage dividers to make it look like an iPhone charger. Power switch, and over here is a bicolor LED which will display red or green depending on whether the power output from the E-fuse is good or bad. There's also 2 TVS diodes. So over here is the 12 volt TVS diode on the input power, and then the 5 volt TVS diode on the output power. Then to build a whole strip of these things, I can just daisy chain them together, like so. So here it is mounted in a laser cut acrylic case. The case kind of glues together, plus it's got screws going in through the top, screws coming up from the bottom to hold everything together. Here's a 4-port version. So I've got 2 5 volt USBs and 2 12 volt. See the top, back. That's it. Gonna mount it. Okay, it's time for a little demo. So I've got the power supply here. It's hooked up via some reasonably heavy wires over here to my Fluke multimeter. It's currently off. The current limit is all the way up. If I turn it on, 5.11.5-ish volts, so about the 5.12 volts that I had anticipated, working as expected. Now let's try to put some resistance. So I have this big resistor. This is a 50 watt 2 ohm resistor. I can trust you can do the Ohm's law on that, figure out how much current that's going to draw. It's going to be a considerable amount. Hook that up. So you notice the voltage drop. So that's partially due to the this wiring here. So even though this is relatively heavy wiring, it still does have a resistance, and when you draw a lot of current through it, it still is going to have a voltage drop. So we're about 4.9-ish volts. We've lost about 200 millivolts resistance going over here because we're measuring at the point of that power resistor. The power resistor it's starting to get hot. Pretty soon I'll be burning my thumb on it. We still got a green light because we're still not within the current limit. If we dial this down, let's get where you can see it. Dial the current limit down. Right there. So that point right there is the trip point of the E-fuse. Now even if we remove the load, the E-fuse is going to stay tripped, and it's going to stay tripped until we power cycle it. So it's good now. If we apply the load, trips immediately. That's great. That's exactly what I wanted out of my overcurrent protection. So here's a shot of my workbench. Please excuse the mess. There's a lot going on. But you can see I've mounted a 4-way strip here. This strip has 2 5-volt supplies, like the ones that I've just gone through in the schematic. And it's also got 2 12-volt supplies. The 12-volt supply, I'm not going to talk about the schematic because it's identical to the 5-volt supply without a voltage regulator. So we're just taking the 12-volt that comes in and we're running it through the E-fuse and the crowbar. Whereas the 5-volt ones, of course, there's a regulator, an E-fuse, and a crowbar. So yeah, so I can plug in 12-volt devices and I can turn them on and off. I can plug in my 5-volt devices. I also bought one of these cheap watt meters off of eBay. So this thing tells me voltage, current, and then computes watts from it. And that's kind of nice because you can see how much all of my strips are drawing at the same time. So like right now I'm running 1.5 watts, which is actually going to power a webcam that's watching my 3D printer. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.